Hello and welcome to Algebra 2 Lesson 53. In this video, we're going to learn about applications of rational expressions. All right, so at this point, we should be very comfortable with solving word problems. All we're going to do in this lesson is look at some examples where we deal with word problems where we have to set up equations that have rational expressions involved. So not any more difficult than what we've been doing in the past, just a slight variation. And I just want to note that we did cover this in Algebra 1. It's just something we recover in Algebra 2, so we make sure we fully understand something like this before we get into something more challenging. So I want to start out with this problem here. So we say that a riverboat travels 75 miles against the current in the same amount of time as it goes 125 miles with the current. If the speed of the current is 5 miles per hour, what is the speed of the boat in still water? So what are we trying to find? We're trying to find out this right here. What is the speed of the boat in still water? So meaning if there was no current at all. Well, to do this, we need to think about our distance formula. Let's scroll down and think about the distance formula for a second. Distance is equal to the rate of speed multiplied by the amount of time traveled. We all know if we're in a car, and I use this example all the time, and we're driving, let's say 30 miles per hour, that's our rate of speed, and we do this for, let's say 4 hours, what's the distance going to be? We could work that in your head. Just do 30 times 4, that's 120. This would be 120, and then for the units, it would be miles, because we're dealing with miles per hour and hours. So we would go 120 miles in that scenario. Now, let's think about this formula with a nice little table. If we reread through the problem, we have two scenarios. We have against the current, and we have with the current. So we have against the current, which I'll just label as against. And we have with the current, which I'll just label as with. So let's put distance is equal to rate times time, like that. And we'll make ourselves a nice little table. I went over just a little bit, so let's kind of clean that up. Okay, let's make a little line here, and now we're ready to go. All right, so the distance when we're going against and the distance when we're going with. Let's see if we can fill that out. So it says that the riverboat travels 75 miles against the current in the same amount of time as it goes 125 miles with the current. So when I'm filling this out, the distance for against is going to be 75, right? Short for 75 miles. And then with it's going to be 125. Again, it's short for 125 miles. And if you wanted to, you could go up here and just say, kind of slide this over a little bit. This is in miles. Okay, now let's think about the rate of speed and the time. So for the rate of speed, we're going to need to introduce a variable. All it tells us here is that the riverboat travels 75 miles against the current in the same amount of time as it goes 125 miles with the current. Now, it says that the speed of the current is 5 miles per hour, but that's not a rate of speed for the boat and how fast it's traveling. That's just a rate of speed for the current. The main question here is, what is the speed of the boat in still water? So let's go ahead and say that the unknown is how fast the boat is going to travel if there's no current involved. And then we can take this information here, this 5 miles per hour, the speed of the current, and we can add or subtract based on the scenario we're in. So if we say that we're going to let a variable like x be equal to the speed of the boat in still water, then what happens? Well, if we're fighting the current, which again, the current, let me just kind of make this on a side note, the current is what? It's 5 miles per hour. So if the rate of speed in still water is x, and I'm fighting the current, then I've got to subtract 5 away from whatever x is. Let's just say, and I'm not saying this is the answer, let's just say the boat goes 30 miles per hour in still water. Well, if the current is 5 miles per hour and it's fighting us, well, then we're going to take 30 minus 5 and say we're going 25 miles per hour if we're going against the current. So I would subtract 5 away here. Now, when we go to with the current, now the current's pushing on the boat. It's making us go faster. So I would add 5. So I would have x plus 5 here. So now we have our rate done. So now let's think about time. So all it tells us as far as information is that the two times are equal. It says the same amount of time. Let me highlight that. Same amount of time. But it doesn't give us a time for either one. But fortunately, with the distance formula, if you have two of them, you can get the third one, right? Through doing a little bit of manipulation. So let's erase this for a second. And let's just scroll down a little bit. If I wanted to solve for time, which is what I want to know, and I have distance equals rate times time, I could divide both sides by r, and I would have time on one side of the equation by itself. So time is equal to distance divided by rate. I have a distance here of 75. I have a rate of x minus 5. So my time for this one, going against the current, is 75 divided by x minus 5. For with the current, it's 125, which is the distance, divided by the rate of x plus 5. So now we're beginning to see what we can do here. We've got our table filled out, so we have all the information we're going to need to gain a solution. The main thing here is that it says the two times are equal to each other. So the time here, which is represented with 75 over x minus 5, is equal to, or the same as, this time here, which is 125 over x plus 5. Again, the way I'm getting this, in the problem, it says in the same amount of time. So again, the two times are equal, so that's how we get our equation. So now all we need to do is solve this equation for x, and remember, x is representing the speed of the boat in still water. All right, so we can use the LCD method, or we can realize that we basically could just cross multiply here. Whatever you want to do, cross multiplying would be faster. But let's use our LCD method so we get some practice with that. The LCD would be what? It would be x minus 5 times x plus 5. So I'd multiply this by x plus 5 times x minus 5. And over here by x plus 5 times x minus 5. And what is this going to do for us? Well, in this case, this would cancel with this. Over here, this would cancel with this. And so you're left with what? You're left with 75 times the quantity x plus 5 is equal to 125 times the quantity x minus 5. And again, you could have got the same thing by just cross multiplying. If I erase this, what could I have done? If I multiply this by this, that's what I've got here. And then it would be equal to this times this, that's what I've got here. Right? So the easier thing to do in that scenario would have been to just cross multiply. All right, so 75 times x is 75x. And then 75 times 5 is 375. So plus 375. And this equals 125 times x is 125x. And then 125 times negative 5 is negative 625. All right, so what we want to do here, let's subtract 125x away from each side of the equation. So that'll cancel. Now let's subtract 375 away from each side of the equation. So that'll cancel. So 75x minus 125x is negative 50x. And this will be equal to negative 625 minus 375 is negative 1,000. So to finish this off, let's just divide both sides of the equation by negative 50. So this will cancel. You'll have x is equal to, negative over negative is positive, and you can cancel a 0 here. You'd have 100 divided by 5, which is 20. So x equals positive 20. So again, when we have a word problem, we can't just stop and say x equals 20 and say, oh, we're done. It doesn't work that way. We have to think about what this actually means. Remember, x was the speed of the boat in still water. That's what we're trying to find to answer the question. What is the speed of the boat in still water? Well, the speed of the boat, or we could say the boat travels at 20 miles per hour in still water. Now, does that make sense in terms of the problem? Well, a riverboat travels 75 miles against the current. So 75 miles against the current. If the boat travels 20 miles per hour in still water, if it's fighting the current, and the current's 5 miles per hour, that means it's going 15 miles per hour. So to go 75 miles at 15 miles per hour, that would take 5 hours. So it would take 5 hours. Now, it says same amount of time as it goes 125 miles with the current. So in 5 hours with the current, if I go with the current here, I'd take 20 miles per hour and I would add the speed of the current to it. So now it's 25 miles per hour. What would that do in 5 hours? Well, 25 times 5 is 125, so that's accurate, right? It would go 125 miles in the same amount of time as it goes 75 miles. So the boat would, in fact, travel 125 miles with the current in the same amount of time, the 5 hours, as it takes to go 75 miles traveling against the current. So we have the correct answer here. Again, the boat travels at 20 miles per hour in still water. Well, let's take a look at another one that involves this distance formula, or again, a motion word problem. So Jeff traveled to his parents' house by car. On the trip there, he averaged 80 miles per hour. On the trip back, due to road construction, he only averaged 50 miles per hour. If he spent 9 more hours driving on the way back, what was the total distance to his parents' house? So you might look at this problem and just be really confused on how to get started. It doesn't seem as simple or as straightforward as the last problem. But again, if you go back to that distance formula, if you just say distance is equal to rate times time, and you make yourself a little table, okay, this is a great way to just organize your information. So we have a trip to his parents and a trip back from his parents. So there's the trip there, and there's the trip back. So those are your two different scenarios. Okay, so let's write distance here is equal to rate times time. All right, so let's go back up and see what we can figure out. So the first information we're given is that on the trip there, he averaged 80 miles per hour. So he averaged 80 miles per hour. So that is something we're going to write under rate. Now it says on the trip back, he averaged only 50 miles per hour. So let's put those in under rate. So for the trip there, it was 80 miles per hour. On the trip back, it was only 50. Now when we start talking about distance, remember, the main question here is what was the total distance to his parents' house? What was the total distance to his parents' house? So we don't know that. So if it's an unknown, let's assign a variable to represent it. So let's say that we're going to let x be equal to the distance, and this is in miles, to his parents' house. So we put x for the trip there and x for the trip back because the distance is the same. Now, what about time? Again, we saw this in the last section where we said that we could find time by algebraically manipulating this formula. If I divide both sides of this equation by r, I would have that distance over rate is equal to time. So I have a distance of x over a rate of 80, so that's my time for the trip there. For the trip back, I have a distance of x over a rate of 50, so x over 50 is my time for the trip back. Now, how do we set up an equation? The times are not equal like they were in the last problem. We can't say this is equal to this. It's not that straightforward here. We have to read back through the problem and think about this. So Jeff traveled to his parents' house by car. On the trip there, he averaged 80 miles per hour. On the trip back, due to road construction, he only averaged 50 miles per hour. Now, this is going to be the key to setting up an equation. You always look for information that they give you that allows you to do this. If he spent 9 more hours driving on the way back, just stop for a second. We know that the time driving on the way back was 9 hours more than whatever it was driving there. So we know that the trip back is going to take us 9 hours more. So that means x over 50, which is the time for the trip back, would be equal to or the same as the time for the trip there, which is x over 80 plus an additional 9 hours, right? Because again, the trip back is equal to or the same as the time for the trip there, which is x over 80, plus it takes another 9 hours. So this would be the equation that you want to run with. Now, to solve this, I just want to find my LCD. So what's the LCD? If I look at the denominators here, I have 50 and I have 80. If I factored 50, I would get what? I would get 5 times 5 times 2, right? Basically 25 times 2. If I factored 80, 80 is what? It's 16 times 5. So 16 is 2 to the 4th power times, and then again, you'd have 5. So for my LCD, I would have 2 factors of 5, or 25, multiplied by 4 factors of 2, or 16. So this is 400. So it would basically take 400 and multiply it by what? You have x over 50, and then this equals, you'd have x over 80 plus 9, and you're multiplying this side by 400 as well. So this is going to clear all the denominators for us. If I multiply 400 times x over 50, the 400 would cancel with the 50 and give us an 8. So this would be 8 times x, or just 8x. And this is equal to, if I do 400 times x over 80, the 400 would cancel with the 80 and give us a 5. So you'd have 5 times x, or 5x. And then plus, if you did 400 times 9, the quick way to do that, 4 times 9 is 36. Put 2 zeros at the end, so you'd have 3,600 there. All right, so to solve the equation, let's subtract 5x away from each side. So this will cancel. 8x minus 5x is 3x. This is equal to 3,600. We'll now divide both sides of the equation by 3. And we get that x is equal to 1,200. All right, so let's go back up to the top. We said that the distance to his parents' house, or the total distance to his parents' house, was represented with x. We just found out that x was 1,200. So we'll say the distance to his parents' house was 1,200 miles. And it's pretty easy to check that. Again, if you can just move the distance formula around based on what you need, it's easy to check things like this. So we think about averaging 80 miles per hour, and you're trying to go 1,200 miles. That's something you can calculate all the time, right, if you're doing a road trip. So I know that, again, distance equals rate times time. So if the rate is 80 and the distance is 1,200, again, to calculate the time, I would divide the distance by the rate. So what is 1,200 divided by 80? That's going to give me what? Well, it's going to give us 15. So the amount of time for the trip there was 15 hours. So for the trip there, let's just notate that. For the trip there, it was 15 hours. Now what about the trip back? So we averaged 50 miles per hour. So we want to make sure that this is 9 more hours than the trip there. That's how we know we got the right answer. So we would take 1,200 and divide it by 50, and this gives us what? Well, this is going to give us 24. And that's exactly what we want, right? So the trip back is 24 hours. And again, if you look back through the problem, that's what it tells us to expect. It tells us that on the trip back, due to road construction, he only averaged 50 miles per hour. He spent 9 more hours driving on the way back. So on the way back, he spent 24 hours driving. On the way there, he spent 15 hours driving. 24 is 9 more than 15, So we have the correct answer here. The distance to his parents' house was 1,200 miles. All right, let's shift gears for one moment, and we're going to look at a problem that deals with rate of work or work rate. Most of you who have done these type of problems before, you know they're super easy. They're a little complicated to kind of wrap your head around when you first start doing them, but there's a very easy formula that you follow for them, and if you follow that, it's going to be very, very simple for you to get the answer quickly. So it takes Cody 9 hours to tar a roof. Trevor can tar the same roof in 5 hours. If they work together, how long would it take them? So when you work a work rate problem, you think about everybody's contribution in terms of 1 unit of time. So if we're working with hours, our unit of time is hours. So in 1 unit of time, we're thinking of 1 hour. So for 1 hour, we think about Cody as being able to tar 1/9 of the roof. Then for Trevor, it takes him 5 hours. So in 1 hour, he's done 1/5 of the roof. So this is Trevor. So once I have these amounts, I think about, let's add these two fractions together to see in 1 hour, how much of the job would they do if they worked together? So what is 1/9 plus 1/5? 9 is 3 times 3, and 5 is a prime number. So I would multiply this by 5 over 5. I'll multiply this by 9 over 9. We'd end up with what? 5 plus 9 over 45, which is going to give us 14 over 45. So if I scroll down just a little bit, let's get a little room going, we could say that in 1 hour, 14 over 45, this amount of the job is completed if they work together. So in 1 hour, 14 45ths of the job is complete. Now, if we want to see how long it would take to actually complete the job, we could let a variable like x be equal to the number of hours to complete the job. And if you wanted to be more specific on this, I just wanted to kind of shorten it, you could say the number of hours to complete the job if they're working together. So what would I do once I have this set up? I have in 1 hour the amount that working together they have completed. So that's 14 over 45. If I multiply this by the number of hours it takes for them to complete the job, what happens is this times this will give me 1 completed job. So once you've set this up, and I know it can be a little confusing when you first start seeing these, the whole key is starting out by finding out how much they can do together in 1 unit of time. So in this case, it's hours. So we figure out in 1 hour, Trevor and Cody can do 14 45ths of the job. Then we say a variable like x, or you could use y or z or whatever you want, represents the number of hours for them to work together and complete the job. So the amount they complete in 1 hour, so this is amount completed in 1 hour, multiplied by the number of hours, would be equal to or would give us a complete job. So all we have to do is solve this for x, and that's super easy to do. You're basically going to just multiply both sides by the reciprocal of that fraction. And when we do that, if I multiply this by 45 over 14, and multiply this by 45 over 14, you're going to end up with x is equal to 45 over 14. So this is how long, this many hours right here, is how long it takes for them to complete the job if they're working together. So we could say, working together, it would take 45 over 14, that number of hours, to tar the roof. Now, if you do the division on 45 divided by 14, you get kind of a nasty decimal. And to not have to round things, I just leave it as a fraction. But it's about 3.21 if you just wanted to estimate. about 3.21 hours. So a lot of teachers would accept that as an estimate just to make the answer cleaner. But just to be precise, I say 45 over 14, that number of hours. Now, if you wanted to check this, you could add Trevor's contribution and Cody's contribution, and you should end up with one completed job. So Cody's contribution is what? He does 1/9 of the job in an hour. So if he works for 45 over 14 hours, how much is he going to do? This would be his contribution, or Cody's contribution. If we add that to Trevor's contribution, in an hour he does 1/5 of the job. Again, he's going to also work for 45 over 14, that number of hours. So would this equal one completed job? Well, you can look and see that it would. This would cancel with this and give us what? It would give us a 5, so you'd have 5/14 plus. This cancels with this and gives us a 9. So 9/14 does this equal 1? 5 plus 9 is 14, so this would end up being what? This would be 14 over 14, which is 1. 1 equals 1, so that equation checks itself out.